If limits are going to be of any use to us in showing why calculus works, we're going to need to be able to calculate them. And while plugging in numbers and looking at graphs can certainly help, if we want to be rock solid sure of our answers, we need to develop algebraic techniques. So I'm wondering, did the last video give you a bit of déjà vu? We were talking about investigating the behavior of a function around some input value by plugging in numbers closer and closer to that value. But think back to when we first introduced derivatives and then later integrals. That's exactly what we were doing then too, starting with an approximate slope or an approximate area, and then refining our estimate until we settled in on the result we were actually looking for. So, in fact, we were really doing limits without actually calling them that. Which means it probably comes as no surprise that the next thing we need to do is move past just having a numerical or graphical understanding of limits and start thinking of them in an algebraic way. That doesn't mean you should stop thinking about plugging in numbers or drawing pictures. That intuition is what reminds you of what all of this means. But by calculating limits algebraically, we can pin down our answers and see why they work the way they do. So what we're going to do in this video is look at a number of algebraic techniques for finding limits. I think you'll see that a number of the tools from your algebra classes end up being really useful. For this part, we're going to do things a little differently than we've done in past lessons. Usually I like to start with a particular example, especially a real-world application, and introduce the new tool we need by working out that example, introducing the new concept just at the moment we need it. This time though, since what we're trying to do is build a firm mathematical foundation, we're going to start with a more ground-up approach, starting from some basic properties and building up from there. That's the way math is usually presented in most textbooks, by the way, so I think it's worth it to get used to seeing how this sort of thing works. That being said, I won't go as far as proving any of these. If we wanted to do that, we'd need to use that epsilon delta definition of a limit. But if you really want to see the proofs, you can always look them up. So, to start off with, there are two absolute basics that we need to use. First of all, if c is a constant, then the limit as x approaches a of the constant function c is also c. In other words, it doesn't matter what happens to x, c will always be c. It's a constant. Second of all, the limit as x approaches a of the function x is, well, a. Think about that for a second. As x approaches a, what does x approach? Well, a. That should make logical sense. Now, there are a few other basic limit laws that we'll start off taking for granted that tell us how limits of certain functions are related. First of all, when you calculate the limit of a sum of two functions, then your answer is just the sum of the individual limits. And that should make intuitive sense. As x approaches a, if f of x approaches L and g of x approaches m, then f of x plus g of x should approach L plus m. And I've got some great news. It turns out that differences, constant multiples, products, and even quotients all work the exact same way. The limit of a difference is the difference of the limits, the limit of a product is the product of the limits, and so on. That should be a relief. You don't have any special rules like product rules or quotient rules to remember. They just act like we hope they would. Though we do have to be careful of quotients. We have to make sure that the limit of the denominator isn't 0. And one more basic law that we'll need to make use of has to do with continuity. It says that under the right conditions, we can move the limit inside or outside of continuous functions. Think about that a second. Say we have f of g of x, and we want to see what happens as x approaches a. If g of x approaches some limit, say m, and f is continuous at x equals m, then the limit and the function value should be the same. So the limit should be f of m, since f is continuous. If that argument didn't make sense quite yet, try coming back to it after we've done some examples and see if that helps. It might help to see it in action. So in all, we've got two really basic limits and how to deal with sums, differences, constant multiples, products, quotients, and compositions of functions. Okay, what does that get us? Well, think about polynomials. What are polynomials really? Well, when it comes down to it, a polynomial is just an expression built of nothing but addition and multiplication. So, if we have a limit of a polynomial function, say 2x squared minus 3x plus 5, as x approaches -1, if we use our limit laws, we could break up the expression into a sum, or occasional difference, of limits, and then break up those coefficients and powers as just products. And all we'll have left is those two basic limits that we know how to calculate. And notice that when we put it all together, we find that the limit of the polynomial as x approaches -1 is just the same as the value of that polynomial evaluated x equals -1. That's why polynomials are continuous. Now, I will admit, that is a lot of steps just to end up getting the same result as plugging in the number in the first place. In practice, you don't need to break down every single problem this way. If you recognize that a function happens to be continuous, you can just skip straight to plugging in the number you're approaching. We call that direct substitution, since the limit is the same as the function value. That's what we said the definition of continuous was in the first place. And so, as we said, polynomials are continuous everywhere. And not only that, but rational functions, root functions, exponential functions, logarithmic functions, and trigonometric functions are all continuous wherever they're defined. But if there's a discontinuity, all bets are off. We can't just plug things in. We need to take a different approach. Let's look at the example from the end of the last video. The limit as x approaches 3 of the quantity x squared plus x minus 12 divided by the quantity x squared minus 9. This is a rational function. It's the quotient of two polynomials, so it's continuous wherever it's defined. Problem is, x equals 3 is exactly one of those points where it's not defined, because the denominator is 0, so we can't just plug in 3. We have to do something else. Actually, not only is the denominator 0, but the numerator is as well. So this seems to be coming out to 0 over 0. But wait, anything divided by itself is 1, right? So maybe is the limit 1? Oh, if only it were that easy. Actually, you know what? Let's run with that for a moment. Suppose 0 over 0 really were equal to 1. Well, 2 times 0 is also 0, right? So we could rewrite 0 over 0 as 2 times 0 divided by 0. Factor out the 2, and if 0 divided by 0 equals 1, then we now have 2 times 1. So 0 divided by 0 equals 2, as well as 1. So 1 equals 2? That's not good. Something went horribly wrong if we ended up at 1 equals 2. It turns out that for this kind of reason, 0 divided by 0 is notorious in calculus. It's what we call an indeterminate form, because when you have a limit of the form 0 divided by 0, it could actually come out to anything. It could be 1, or it could be 2, or -17, or pi, or infinity, or maybe not even exist at all. There's no way to tell. That's what makes it indeterminate. So when we have a limit of the form 0 over 0, we can't just cancel out 0 over 0 and get 1 immediately, as nice as that would be. Whenever that happens, it's actually a clue that maybe some algebraic massage is what we need. So let's see what we can do. If we factor both of these polynomials, the numerator comes out to x plus 4 times x minus 3, and the denominator comes out to x plus 3 times x minus 3. Okay, so that's why they both came out to 0. X minus 3 is a factor of each. Awesome, so let's cancel them out, right? But wait, if x is 3, then isn't that just 0 over 0 again? That would mean we can't cancel them out. I guess we're just out of luck. But hold on. Remember, we're finding a limit here. And for limits, we don't care what happens at a point. We only care what happens around a point. So when x is approaching 3, that means x is not equal to 3. And that means x minus 3 is not equal to 0. And that means we don't have 0 over 0 anymore. So we can safely cancel them out to 1 and simplify the fraction, as long as we still write that limit notation to keep us safe from dividing 0 divided by 0. And look what happened. By simplifying the fraction, now we have a rational function that does have 3 in its domain, because it won't cause us to divide by 0 if we try to plug in x equals 3. Now the simplified function is continuous at 3 because it's still a rational function, and that means we can just use direct substitution to get our limit. Plug in 3, and we get 7 divided by 6, 7/6. So this is a pretty common way to handle limits of the form 0 divided by 0. Do some algebraic massage to try to separate out the offending factors in the numerator and denominator. Cancel them out to 1 while in the safety of the limit to make sure you're not dividing 0 by 0, and then take a fresh new look at the limit of the simplified function. Now, as for what type of algebraic massage to use, that varies, and it depends on what might be most useful in the situation you have. If you've got square roots, for example, using radical conjugates may help. That's where you switch the sign in between two terms where one or both have square roots in them. Or if you've got a sum or difference of fractions, it might help to combine them into one big fraction with a common denominator. You might even be able to notice a limit you've seen before, play around with it a bit to isolate it, and use what you already know. In any case, as long as you're careful, you won't be in danger of dividing 0 by 0, and you can safely calculate your limit. Now, let's take another look at that rational function from earlier. What if we wanted to find the limit as x approaches -3? We're still welcome to cancel out the x minus 3 from the numerator and the denominator. Since we're close to -3, neither of those will be anywhere near 0. But now the problem is that we still can't plug in -3. We'll still end up dividing by 0. But this time, the numerator is 1. So now we've got something of the form 1 divided by 0. Algebra won't help us here, but a little thinking about the numbers will. Say we plug in a number just a little bit more than -3, say -2.9. We'll get 1.1 divided by 0.1, which comes out to 11. Cool. If we get a little closer, like -2.99, we'll get 1.01 divided by 0.01, which comes out to 101. As we plug in numbers closer and closer to -3, the numerator will always be close to 1, but the denominator gets smaller and smaller, which means the answers get bigger and bigger. In other words, as x approaches -3 from the right, the function blows up to infinity. So our right-hand limit is positive infinity. Okay, how about the left-hand limit? If we do the same thing here, plugging in numbers just a little less than -3, but still approaching -3, then the numerator will still be close to 1, but now the denominator is made of smaller and smaller negative numbers. So as x approaches -3 from the left, the function blows up to negative infinity. So our left-hand limit is negative infinity. And since the left-hand limit and the right-hand limit don't match, the limit as x approaches -3 in general doesn't exist. This is an incredibly useful intuition to have. When you divide by a very small number, you get a very large number. So, when the denominator of a function approaches 0 while the numerator doesn't, the function will blow up to infinity. Maybe positive, maybe negative, maybe a little bit of both, depending on science. Be careful not to take this intuition too far, though, and say something like 1 divided by 0 equals infinity. Why not? Well, you might think I'm gonna say because you can't divide by 0. That's just one of the best known basic rules in all of math. But actually, despite what you may have been told, if you know what you're doing, there is a way to divide by 0 and get an actual answer. Yes, I'm serious. That answer isn't infinity, though. It's actually something way more interesting than that. Now, if that's got you intrigued, I actually have a website that goes into how it works, 1dividedby0.com. I kid you not, that's actually the website. Check it out if you're curious sometime. It actually ties together a lot of things you learned in algebra and pre-calculus classes. But I'm gonna warn you, if you go down that rabbit hole, you have to be really careful. Infinity can be thought of as a number, whether it's positive, negative, or unsigned like 0, but it's not a real number. So it doesn't follow the same algebraic rules as all the other numbers you're used to. And you have to understand, trying to use infinity directly is not going to help you in calculus, and it may actually harm you if you're not careful. Misuse of 0 and infinity is one of the most common things that makes reasoning about calculus go astray and lead to the wrong conclusions. The whole point of limits is to give us a way to avoid those pitfalls by making sure that we avoid dividing by 0 and stick to the real numbers and algebraic properties we already know.